Hi everybody. So this is going to be a question and answer video while we're waiting for the parts to come in for the Pioneer Series 20 M22 amplifier, the Class A amplifier, because like I said, I had to order those parts and I got to wait for them to come in. And this is a holiday weekend and I have a nice free day today. It's nice out, and before I go out and take a walk or go hang out with my wife or something, I thought I'd shoot a little video down here. I've been getting some questions. The emails have really been kind of piling up from my patrons. So I tried to go through and answer all those this morning, but there's a few of them I think would be easier to answer in a video, and it could hopefully be beneficial to the rest of you. So I'm going to answer 3 questions, and one of them deals with connecting the Sencor SG165 to a signal generator. It seems to be something that a lot of people are having a real challenge with, and it's strange because it seems to me like it's one of the easier things to do, but maybe there's a few things that maybe just needed to be clarified. So I'll do that. I'll demonstrate it real quick. I'll dig out that Marantz 2015 and kind of use it as a test subject, and we'll get that done. And then I have 2 other questions concerning op-amp scaling circuits that I made in 2 of my projects. One of them being for the Antique Wireless Association capacitor leakage tester, how I have the analog meter and it has 3 different scales. I'll show you a schematic and explain that a little bit. And the other one is for the DIY curve tracer kit that I did. And there was just a couple questions. A few of you were trying to build that, and there were some things that weren't shown in the video that you were interested in, so I'll try to explain those. So those 3 things, and hope you enjoy it. All right, let's get started. Okay, I'm not really quite sure why people get so hung up on this. It seems to be a big challenge to a lot of folks who are trying to get this to work. So I am going to just demonstrate in a quick clip here how to connect a Sencor SG165 to an external RF signal generator. Now, first of all, you need to know that you can actually do a stereo output using the RF generator inside here. And the way you do that would be to just take this up to where it says RF. So you would turn it up here, set it to whatever frequency you want, and then modulate, just come out of here and go into your antenna jack, and there you go. But the big question I get is, how do you use this as just a standalone multiplex stereo signal generator that can drive a signal generator, that RF generator that does not have multiplex? So this is how you do it. You need 1 coax cable. You need an RF generator that's capable of external modulation, external FM modulation, which we have. So any of this series of HP, this seems to be the most common that you see, is these HP, 8657, 8656, all the different versions of these. Some of them have knobs instead of buttons. They're all the same thing. But what you're going to do is you're going to select FM external, or just hit external and then FM. And this should light up to tell you that you're using external. And you're going to go into the modulation input-output jack. And you're going to come out of the all signals output jack of your Sencor SG165. Rotate the knob to multiplex signal. See MPX signal? You're going to select that. Make sure that the modulation is set to standard multiplex. And then these 3 controls are what going to control the left channel, the right channel of the 400 hertz tone that you're going to hear, and your pilot tone. So you can actually turn the pilot signal off, and that'll switch it into mono. So when I hit that, if you go to the, let's see if I can get everything in the shot here. So you can see if I have the pilot turned off, there's no stereo indication. If I turn it on, stereo indication. Now going over to the scope, which you can just barely see over there, see if I can get it all in there. Look at the scope. If I turn the left channel off, you see it goes down. Right channel off. If I have pilot off, then turning either one of them off just gives you your left plus right. See that? And the amplitude goes down, but both channels stay on. If I go with the pilot tone, that gives us the stereo, and now you have this. Okay, very simple. One connection. The output of this goes to the modulation input of this. That's it. Now, for your signal generator, you just set it to a frequency on the dial. I'm at 98 megahertz right now, and you tune your dial to 98 megahertz. You should get the stereo if you have the 19 kilohertz pilot on. And you can set the modulation, almost to max, and it'll work just fine. If you notice, it's a low signal. Even with everything turned up the whole way, these signal generators notoriously have a low output of signal. That's just the way they work. And that's really all there is to it. I can't really explain too much more about, that's all there is to it. You come out of this and you can see the wire here. I'm just going into the FM antenna jacks. That's it. I just go into the FM antenna. And you may have to crank the signal up some if you have a bad mismatch with your cabling and whatever. And remember that, a multiplex signal has to have a lot more drive than a mono signal. But that's really all there is to it. If there are any other further questions from that, just leave them down in the comments. But that's it. That's all there is to it. Hope that kind of clears that up. And just to show you that it does work, I've unplugged the antenna from there and plugged it into the output here. And then I just moved the knob from multiplex signal up to RF, left everything else the same, and take a look. We have stereo signal, and again, left, right, pilot tone off and on, and this becomes a self-contained thing. Now, again, if you're doing dial alignment, this is pretty close. It's not going to be as good as a synthesized signal generator. That's why I do this. That's the advantage of that. But this is more than capable. It doesn't have as high of a signal output, but it does work. So there you go. And you can see you can kind of tune on and off signal with that. And there you go. Very simple. Okay, next, let's look at the capacitor tester. And the purpose for this is it tests capacitors for leakage. So if you have a film capacitor or one of those old paper foil capacitors, you can check for any kind of leakage current, because that's one of the failure modes of a capacitor. On electrolytics, this can put a current limited voltage across an electrolytic capacitor to help the capacitor to chemically reform, because sometimes when capacitors sit for a long time, the chemistry changes in them and it causes them to develop leakage. And just by passing current through them for a while, the chemicals will realign themselves and it will turn into a good capacitor. And it doesn't necessarily mean that it's a junk capacitor and it's not like a picture tube rejuvenator where it's like a temporary fix. It actually can form the capacitor so that it will work like brand new and last like brand new. Just depends on the cap though. A cap that is depleted, that is worn out, that the chemistry has leaked or dried out, this won't fix that. So it's not for that. It's only for forming capacitors that have been in storage or sitting for a long time, that are still in good condition. All right, so that's really not what this is about. The question was, I made a modification to the original circuit from Antique Wireless. And by the way, I ordered another product from them, and we're going to be doing a video on that real soon. And I'm pretty excited about it, and I think some of you will really be excited. You'll want to do this project also. But anyhow, one of the changes I made on this was the range. using an analog meter, and this is just something I wanted to do just to see if I could do it. Normally, there's a pair of, just a connector you would put here, and you would take your digital meter and you would set it, to the millivolt range, and you can read, volts equals milliamps sort of thing. And that works really well. And there's really no reason to deviate from that unless you're like me and you just want to mess around. But some of you wanted to tinker around and add this analog meter feature for the leakage. It's kind of nice to watch the actual needle move on the meter. So you can kind of watch it slowly, form the capacitor, or as the cap charges, you could see the current drop and so forth. But the problem is, when you have a meter like this, no matter what meter you get, it's never going to work in all instances. In other words, to have a meter that's accurate at very low current as well as higher current is really hard to do. So what you have to do is you have to build what's called a scaling circuit, or allow it to change the scale of the meter. So if it's in this right here, then 5 volts is going to equal 50 microamps. So this reads in microamps when it's in the most sensitive scale. This one times that by 10, or multiplies that by 10, and 5 volts would equal 500 microamps. And then, of course, the highest one would be 5,000 or 5 milliamps. Basically, you don't, if you have 5 milliamps of leakage on a capacitor, any cap, that's way too much. So that's a good range for this to be. So how did I do it? You could see, here's the original board. You don't need any of this. And this is a self-contained circuit, and all you need is to connect the connectors and switches and one external potentiometer, and you have everything you need. And this is how it comes from Antique Wireless. You get the board, and you get a printout that shows you the order list from Mauser, that you can order all these components from Mauser. And that's it. And I don't know what this diode is doing in here. Something fell. So anyway, that's what that is. Now, the part that I changed, or I added, was this. So there's a small transformer. There's a small linear power supply, and it's regulated with two 9-volt regulators. One's a 7809 and one's a 7909. So it gives you a plus and minus 9 volts. And we use that for our little scaling circuit. And you can see it's simple. I actually used an LM308, and I can zoom you in on the board how it looks. It's a very simple board. There's the LM308. There's the 2 pots to get it set perfectly for the 2 more sensitive scales. And let me show you the schematic. Let's zoom in as best we can. And if you want to stop the camera and just take a screenshot of this, go right ahead. So it's very simple. This is nothing but an op amp. We're going into the non-inverting input, and the normal signal is 1 volt equals 1 milliamp. That's the way this board here is configured. So that's our starting scale. So basically, if we just do a pass-through signal out to the meter, if we get 5 volts, because this is a 5-volt full-scale meter, it would give you 5 milliamps of leakage current. But we want to be able to scale that down. And that's what this does. And really, all we're doing is we're interrupting the feedback. If you look, when you have a non-inverting amplifier like this, you come into the non-inverting input, you have a plus and minus power supplies, and then you have your feedback that will come from the meter circuit, and it'll loop back through into pin 2, which is the inverting input. That's your feedback loop. Normally you would just put a resistor in there. But in this case, we're switching different resistors based on what kind of gain you want this. All you're doing is you're changing the gain of this little op amp, the actual DC voltage gain of this circuit. So for the full scale, we're putting a 10K resistor in there. And then for the 500 microamp and the 50 microamp, you have to put larger resistors. So I used a 20K potentiometer and a 100K potentiometer, which both of those give you lots and lots of adjustment. And these are both 20-turn pots, trimmer pots. So all you do is you can put a known resistor in the test leads, these test leads right here, clamp that in, and that will give you a known leakage at a known voltage, and then you just set the meter using these pots for that scale, if that makes sense. So for instance, if you put a resistor in there that the voltage, and then you set the voltage, that the voltage divided by the resistance is going to give you a leakage of 250 microamps, let's say, then you would start the thing up, and then you would just adjust this pot until you read 2.5 volts on the meter, and your scale is set. And you do the same thing for the 50 microamps. You just put a higher resistance in there and set your voltage and everything, and then adjust this. And that's how I did it. It's very easy. So really, you can buy these things for less than $1, and then a little perf board, 2 pots, 1 fixed resistor, and then I used a rotary switch because you can buy these online very inexpensively from eBay, Amazon, whatever, and they're very inexpensive. The one I bought is a 3-position. The schematic symbol I had was only for a 6-position, so that's why it looks like that. But you could actually add more resistors if you want more scales, depending on what feedback you put in there. That's it. And since it's DC, you really don't have to worry about any frequency related component, because this is a DC level. So the op amp just operates with just straight resistive feedback. So it's pretty easy. That's all there is to it. And you can see the meter is at the output of this, and there's plenty of output on these little op amps to drive this meter, because the meter movement that I uses very, very low current. So if you had a meter that drew more current than the op amp could deliver, then you would have to have a little voltage follower circuit using a transistor or something. And you can look those up, but you're not going to need that. Most of these analog meters just draw microamps of current, so you can directly drive it with this. So that's it. That's all there is to it. Okay, last but not least is the curve tracer project that I did. And this was a lot of fun. I really enjoyed this. And we made a couple modifications to it. Number 1, to make it more accurate. And number 2, to make it easier to match transistors. Now the first question was pretty easy. I put 2 sockets on here so that you can have 2 transistors at the same time. And I used it's a 4P double throw switch with center off. Is how you 4P DT with center off. So when this is in the middle position, none of the contacts are made. You flip it up to here, there's 4 contacts that are made in this direction. If you flip it this direction, there's 4 contacts made in this direction. And essentially all we're doing is we're passing the signal from these 2 sockets through 1 pair of those switches. And then for the LEDs, I put an LED indicator light for each channel, and I used the other contacts to pass the voltage for the LEDs through them. So that way, you can just look at where the switch is, but the light indicates directly just a quick glimpse. You don't really need these. I did that to just make it a little bit easier to see. And that's all that's doing. Now to power the LEDs, it's very simple. You have to pick what type of LED you're using, figure out what your voltage drop across that LED and what current that it draws, and then you can just pick right off of the power supply and calculate the resistor size to give you that voltage drop and that current for the LED. Usually it's going to be like a 1K to a 2K, something like 2.2K resistor will work fine. It's not super important because if you get a bigger resistor, this will just be a little more dim. Who cares? As long as it glows and you can see it, that's all we're looking for. Nothing fancy. And again, you don't need this. You can use a single socket. The only reason I did this is to make it easier to toggle back and forth. Now, somebody made a comment that by passing it through the switch, the resistance is going to be added, it's going to add the resistance to it, and it'll make the curves be less accurate. Possibly, I mean, you're using a 1 ohm precision resistor to read the voltage drop, but really, I mean, you're talking maybe a couple milliohms on the switch, unless it's a bad switch. The wire runs are pretty short, and again, solid copper wire, good quality, very, very insignificant change that it's going to be. And remember, we're really not trying to characterize an exact thing with this. This is really to see the curves, to get a rough idea of what the gain is, if it's high gain or low gain, and more importantly, to compare two transistors to see if they're the same. That's really what this is best at doing. If you want to characterize a transistor, you're better off with a full-blown curve tracer that you can adjust the current through the transistor, the current stages through the transistor, or current limiting, and the different voltage sweeps and all that. You need a real curve tracer. This one works great for just matching small transistors. That's what we're doing. And it is pretty accurate, believe it or not. When I compared this to my big curve tracer, I was shocked how close this thing tracked, at least the way this one's put together. Now, a couple of notes. He asked, I'll look at the schematic in a second, where did you get the voltage to drive the scaling circuit? Because again, we did a scaling circuit on this. And really, this already has a plus and minus 15 volt supply that is more than adequate to drive this and drive that little op amp. So I just simply picked off the 15 volt supply. Very simple. I believe, if I remember, this resistor, which is a 1K, I think, or no, 4.7K, I think this is what I was using for the dropping resistor, possibly for the LEDs. I could be wrong, I don't remember. But there it is, and here's the op amp circuit, and I'll zoom you in on it. Let's get this out where we can see it. There you go. It's very simple. Again, I try not to make anything too complicated. And this one, I am using an LT1632, and that is a op amp that is suitable for test equipment. This is some pretty fast signals. You might think that, the low frequency of the sweeps on this are, you don't need anything, but you have to understand the retrace and everything is very quick, very fast. There's very abrupt changes. And if you looked at the FFT, you will see that there are frequency components in there that are a lot higher than the sweep frequency of this thing. So basically, you need a pretty fast op amp. I tried using like an NE5532 and a TL081. They worked, but they had little artifacts in the sweeps that you could see. So I had to use this and then use a little bit of filtering to get it to look perfect. And that's how I did it. Now we'll look at the schematic. So here's the schematic of, this is the one that comes with the unit. This is what you get when you order this little board, this little kit on eBay or Amazon, wherever you get it from. And this section here is the part that I added. You can see right there. And you see how you have plus and minus 15 volts at the input, and then it's dropped down to 6.2 volts plus and minus. That's the 15 volts that I'm using to drive this. And you can see I'm just coming straight off of this going into the op amp. So that answers that question. As I said, with the switches, it's very simple. I can show you the bottom of the board here, how it's wired. There it is. If you want to stop the video. and look, but that's how it's wired up. I don't know if the angles, I'm trying to look through the viewfinder and see if you can see everything. And then there's how it goes in the whole, there's the whole shebang there. Okay. And there's the op amp. This is the filter network with the feedback. Here's the pot that we use to fine tune the adjustment. And really all I'm trying to do is I'm trying to get that scale to be exactly 10 millivolts equals 1 milliamp. And that makes it a lot easier to read on your scope, because there's certain, the problem is when you're looking at really tiny signals on an oscilloscope, the input impedance on a scope is relatively high, and the input channels on an average scope, especially these new digital scopes, which I don't recommend for this application, because XY mode is always grainy and pixely. It always ends up having a lot of noise in it. By scaling this up by a factor of, what did I make it, a factor of 10, it allows you to set a scale on your scope that's less noisy. So it makes the traces look a lot clearer, and that's why we do this. And again, it's just similar to that one that we did on the capacitor tester. It's just an op amp, and you're setting the gain to give you the scale that you need, and we're making it adjustable. Make this like, again, a 10 or 20 turn pot, and you can really fine tune it until it's perfect. And that's easy to do because you can actually look at the 1 millivolt equals 1 milliamp at the input, and then you can measure it at the output. And the whole idea is you adjust this until the amplitude of this trace here is exactly 10 times the amplitude of this trace. So they'll both be, go into dual channel on your scope, and you should be able to do that. And that's all I did. So I hope that explains it. All right, so that's it for this little video. I hope it helped you all out. And one last question is, I keep getting these recurring questions about some song that you heard on one of the videos, and I really just don't know what you're talking about. So, I don't know. We'll have to find out. Catch you next time. Peace, joy, happiness, and good health in your lives. We'll see you again real soon with part 2 of the Series 20 M22 Pioneer Class A amplifier. Say that all 5 times fast. Take care, everybody. Bye-bye.